transformation. From V to W. If for all vectors xy in V and a scalar from F, we have a t of x plus y is the same as the function applied first to x and y and then added, and b, the function applied to a scalar times x is the same as x times the c, the scalar, times the function applied to x. Alright, so a linear transformation is just a function in vector spaces that has these two nice properties. Now let's look at the theorem that we will prove here, and then we'll probably get a few more definitions. If you want to check in the book that I've just told you, that is Theorem 2.1. Again, let V and W be vector spaces, and T of V to W be linear, so we can use our new definition. Then NT and RT are subspaces of V and W. Respectively. Basically, N of T is the kernel, or I think it's also called null space, which is why there's an N of T, and that is all the vectors of V that the function maps to 0 in the target space. So this is V and this is W, and this is our 0 in the target vector space. Then we have a subspace in here where every entry goes to 0. Of course, we also have other entries that go to somewhere else in the target space. Similarly, R of T is the range or image of T, and these are all the values that can be reached if you go through all of the entries of V. Now, what do we want to prove here? We want to prove that these are subspaces. So we need to know or remember what a subspace is. separate video about vector spaces and subspaces, but let V be vector space and W a subset of V. Then W is a subspace of V if and only if all the way 3 conditions hold for the operations defined in V. So the first thing that needs to be true is that the zero vector is part of the subset. This is a bit confusing here because here this is the subspace and here these are both vector spaces, so don't be confused by that. Okay, then x plus y need to be W whenever x is in W and y is in W. So I think you say this has to be closed under addition. And also Cx needs to be in W whenever C is F, so the scalar in the field, and X is in W. So that's closed under scalar multiplication. Okay, so we need to prove these 3 conditions, and then we know that W in this case is a subspace. And start with, did I already write proof? No, okay. Let's start with the proof. First part. Show that the kernel is a subspace of V. Part A is zero vector in T, or also written as 0 in T. For this to be true, we need T of 0 has to be 0 because everything in N of T has an X where it goes to 0. Oh no, everything in NT maps to 0. So if 0 is in there, then we have to insert 0 for X, which gives us this equation. So that's what we need to show for this to be true. Now, because T is linear, plus y is t of x plus t of y, right? And for the special case, x equals 0, because this equation holds for every x and every y. So for the special case x 0, we can choose that. We get t of 0 plus y equals t of 0 plus t of y. And 0 plus y is obviously just t of y. And now if we subtract t of y on both sides, we get that t of 0 has to be 0. And therefore 0 is in the kernel. Okay, so that was part A of showing that this is a subspace. Now let's look at part B of the addition. Alright, B. Show that x plus y is in T whenever x and y are in T. Let's take some arbitrary xy out of the kernel, which we do in the NT. Then from the definition of the kernel, we know that t of x is 0 and t of y is 0 as well. Now because t is linear, we have 0 plus 0 equals t of x plus t of y, and that is the same as t of x plus y, and that's because it's linear, we get this equal sign here, and so this also has to be 0. And if this is 0, then this here is in n of t. And the last equality, so the last equal sign here, gives us x of plus y is also in the kernel. Okay, so that was part B. And now part C. Show c of x is in of t whenever c is a scalar and x is in the kernel. Take x from the kernel, then we know that t of x is 0, and because t is linear, we know c of c times t of x is the same as t of cx. And t of cx is c of t of x. But t of x is 0, so that's c times 0, and that's 0 itself. Which means t of cx itself is 0. So cx is part of the kernel per definition. Okay, so now we have shown parts A, B, and C of a subspace. So we have now shown that the kernel is indeed a subspace of V. And now we can do it similarly for the image. Now second, show that the image of T is a subspace of W. 0 in the image. Every vector space has a 0 vector, and so 0 exists in V, and in the above part we have seen that t of the 0 is indeed 0. So 0 is part of the set of all mappings of x's for x of v, which is the definition of the image. If only we use x equals 0 in here. So 0 is indeed in the image, because we know that 0 maps to 0. Alright, part B is x plus y in RT. Oops, under the condition that x and y are part of this image, similarly to above. Take x and y from the image. Then exists a vector in V where t maps from this vector to x, and same for y. It exists a vector v2 with t of v2 equal y. Again, because t is a linear transformation, we have x plus y equal t of v1 plus t of v2. These are just the separate definitions up here. And now, because this is a linear transformation, that's the same as t v1 plus v2. Let's again mark this in red. So it's linear. That gives us this equality. And the whole equality gives us t of v1 plus v2 is x plus y. And v1 is a vector space, and as such closed under addition. That's one of the properties of a vector space. And therefore there exists an entry in V that maps to x plus y, and this entry is precisely v1 plus v2. So x plus y is in the image. And the last part, C, is Cx, part of Rt. Whenever C is a scalar and x is an Rt, start by taking, this doesn't look like take, start by taking x out of Rt, then it exists a vector v with t of v equal x, just by definition. Now we get Cx equals C of TV just by replacing TV x with TV in this equation, and that is the same as T of CV, because again T is linear. And because V is a vector space, CV is in V, because it's also closed under scalar multiplication. And so we again have an origin vector CV. So Cx is T of CV, and that makes it part of the image, which is defined as T of V for all entries of V. So we have also proven now that Rt is a subspace of W. So we're done with the theorem. Therefore, both Nt is subspace of V, and the image R of T is subspace of W. And now we can draw a little box, because that means the proof is done. I'm just zooming out a bit so you can see what we did. And I think this was a neat little exercise to see and get familiar with what a linear transformation is and how you would use the properties up here that you get. And you can also see that it has many more nice properties, such as that the kernel and image are subspaces. And the next few bits in the book then tell you more about what you build up on the kernel and image, etc. Because you can show some interesting stuff with those. But that is part for the next video. Thank you so much for watching, and I'll see you in the next one. Bye!